The study aims to provide an impartial, comprehensive comparison of two typical multi-storey office buildings across a number of aspects for different structural solutions to provide cost and programme guidance for design teams and quantity surveyors when considering the options available during the design and selection of a structural frame. Two typical office buildings will be considered, Building 1 being a low-rise out-of-town business park office building, and Building 2, an 8-storey city centre office building. We'll go into a bit more detail later on those. As decisions on frame material and configuration will be based on a number of factors, the structural characteristics, programme and buildability implications of each of the framing options will be considered alongside the cost implications of each. In addition, the cradle-to-grave embodied carbon implications of each of the framing options will also be considered for Building 2 only.
Okay, so the first building that we will consider is a typical speculative 3-storey business park office building with a gross internal area of around 3,200 metres squared, plus a rooftop plant enclosure. It is representative of a low-rise building in an out-of-town location and is rectangular with a floor plate width of 18 metres to provide open-plan internal space, as shown in the indicative cutaway and architect's impression images. The clear floor-to-ceiling height has been set at 2.8 metres, and the building contains one central core, 2 lifts, and an external metal estate stair. The external envelope has been assumed to be brick outer skin construction supported by a steel angle off the slab edge, with an inner leaf of cold-rolled steel metal framing built directly off the slab, with an allowance for windows at 35% of the facade area. The building has been assumed to have mixed-mode ventilation, and the floor-to-floor heights include for a 150mm ceiling and lighting zone and a 150mm raised floor zone.
So, as Rachel mentioned previously, the building was designed to represent a typical office that you might find in an out-of-town business park, being 3-storey with an area of 3,300 square metres and overall planned dimensions of 60 metres by 18 metres. We chose to use a design grid of 7.5 metres by 9, primarily because it's a common grid in this type of building, and although a 7.5 metre square grid is also common, there's a lot of previous cost data on that grid size which we didn't want to replicate here. That grid size also lends itself to open plan office layouts. It provides good natural lighting and also helps to achieve natural ventilation, although it is on the upper limit for that. As far as structural options were concerned, we chose 4 of the most common options used in office buildings. These were steel composite beams and composite slab, steel frame with precast slabs. Option 3 was reinforced concrete flat slab, and the 4th option was a post-tension variant of the flat slab. So these 4 options were taken forward and designed in enough detail to enable costing and programming of the construction. In terms of loadings, for superimposed dead loads, we assumed a raised floor for power and data distribution, along with suspended ceilings and services, giving a combined superimposed dead load of 0.85 kilonewtons per square metre. Imposed loads were assumed at 4 kilonewtons per square metre for office areas, with an allowance of 1 for partitions. And although BCO loads are lower at 2.5, many offices still use the higher loading to ensure flexibility of future use. In terms of stability, core construction was assumed to be steel cross-braced framing with blockwork infill for the steel-framed options and the concrete core walls for the in-situ concrete frames. Foundations were assumed to be pad footings with a bearing pressure of 200 kilonewtons per square metre, and ground-bearing slabs were assumed throughout. For services, the ventilation system was assumed to be mixed mode, where natural ventilation is supplemented by mechanical ventilation during periods of high or low temperature. Steelwork Solutions assumed a 300mm minimum service depth beneath the beam, and the concrete flat slab options assumed a 600mm clear zone beneath the slab. The floor ceiling height was set at 2.8 metres, with the floor zone then determining the final floor-to-floor height for each option. In terms of roof construction, steel-framed options switched from composite slab to lightweight metal roofs such as a D60 structural deck. However, concrete-framed options retain the concrete slab at roof level. The main reason for this is that many contractors prefer to keep one subcontractor on the frame rather than changing to a steel subcontractor late in the programme. In terms of results, I won't go into details of the steel sizes or slab depths, but I'll look instead at the impact on floor-to-floor heights. The steel composite option came in at floor-to-floor height of 4,030 millimetres, which was virtually identical to the concrete flat slab at 4,025. The deepest option was a steel precast at 4,200 millimetres, and the shallowest by whisker was the post-tension slab option at 3,950 millimetres. These depths then set the overall building height and allowed items such as cladding costs to be assessed for each option. Raj.
Thank you, Fergal. Okay, clearly programme and buildability is an integral part of the comparative study, and we took a sort of a holistic approach to programming in that we've clearly kept as constant as possible all the elements that were common to the complete building construction program through to completion. Program durations, for example, for the ground floor slab, 2 weeks, 4 days, were kept constant, as were external facade and internal fit-out, which we've based at 18 weeks per floor. The internal fit-out is assumed to commence on the ground floor and progress upwards, and we've assumed 3-week lag between each floor. The substructure considerations for the steel and concrete were 9 weeks for the steel option and marginally longer because of the higher volume of work for the concrete option, because of the heavier frame. In overall terms, what we have here is a program summary of the 4 options that Fergal has just outlined. The steel composite frame was 6 weeks. These are all working weeks on all programs. The precast concrete, nearly 7 weeks, and nearly 9 weeks for the RC traditional, and the 8.5 weeks for the PT option. In overall terms, we have both steel options at around 45, 46.5 weeks, about 48 for the concrete options. Both steel options therefore have similar durations for the substructure frame and upper floors. The steel composite has a quickest frame and upper floor duration. Steel decking is, we found, quicker to load out, so the logistics of loading out the steel is marginally quicker than precast planks, and therefore both steel options have similar overall durations for laying and distributing the steel decks. However, this composite is, as I say, marginally quicker. The post-tensioning option has a slightly quicker frame and floor duration due to the lower quantity of reinforcement placement within that option, and is therefore marginally quicker on the RC. Across all options, the steel frame therefore is a slightly faster method for this type of building. In terms of logistics, we outline here the steel option, which we've assumed could be built in 4 phases, and we're building each phase to its full height before moving on to the next phase. The craneage strategy for the steel has been assumed to be a mobile crane, and placement of concrete has generally been by pumping. For the concrete options, we have looked at a tower crane and looked at a two-zone or two-phase strategy, and this is on a floor-by-floor basis. So the formwork would go after it's been struck from one level to the same level on this floor, and the tower crane has been assumed to be a saddle tower crane in this instance, assuming there are no oversailing issues. And now I'm going to hand you back to Rachel.
Okay, Gardner and Theobald prepared estimated costs for the study, which are based on market testing and recently tendered projects. All costs in this presentation are at fourth quarter 2013 prices and are based on construction in the City of London. However, they can be adjusted for different locations using BCIS location factors. Fees, VAT, project contingency, FF&E and AV allowances, Section 106 and 278 costs, and so on, are excluded from the study. The study recognises the importance of considering all elements of the total building cost, not simply the cost of the structural frame, as some elements are affected more by the frame choice than others. In particular, substructure, which is affected by the structural layout and weight of the frame, roof, the construction and configuration of which may change depending on the frame choice, and external envelope, the area of which will vary depending upon the achievable floor-to-floor height, along with all other vertical components of the building. To make sure that these variables were fully captured, the study considered whole building cost rather than just structural frame cost, and the substructure, roof, and external cladding costs were assessed for each option rather than including constants. Some items were, however, assumed to be constant across all of the options, as they were not considered to be affected by the frame material or configuration, including stairs, internal fit-out and finishes, and the mechanical and electrical services. It was assumed that a suspended ceiling is required across all frame types, with boxing in to internal steel columns and plaster and paint to internal concrete columns included. A further key variable to be reviewed when analysing the costs of alternative framing options is the impact of each on the achievable construction programme. In this study, the varying construction programmes and logistic strategies produced by MACE were considered when determining the preliminary cost allowances for each frame type. This slide sets out the key costs for the 4 frame options considered for Building 1, all expressed as a cost per metre squared gross internal floor area. Looking at just the frame and upper floor costs of each of the options to start with, it is clear that there is a significant variance in cost across the different frame options. The steel composite beam and slab option has the lowest cost, at £140 a metre squared gross internal floor area, with the cost of the other 3 framing options ranging from £150 to £153 a metre squared. A review of the impact of frame selection on the substructure costs also shows that the steel composite beam and slab option has the lowest substructure cost at £52 a metre squared, followed by the steel and precast concrete option, the post-tension concrete flat slab option, and finally the reinforced concrete flat slab option at £67 a metre squared. The impact of the construction programme and logistics strategy for each option also impacts on the preliminaries costs for each frame type, with the 2 steel framing options benefiting from lower preliminaries costs due to their shorter construction programmes. Overall, the steel composite beam and slab option has the lowest total building cost at £1,535 a metre squared gross internal floor area, followed by the steel and precast concrete slab option. Post-tension concrete flat slab option and the reinforced concrete flat slab has the highest overall cost at £1,628 a metre squared. As noted, the steel composite beam and slab option has both the lowest frame and upper floors cost and the lowest total building cost. It also has the lowest substructure cost of all Building 1 frame options due to the lighter frame weight, lowest preliminaries costs due to the shortest construction programme, and also benefits from low roof costs due to the use of a lightweight steel roof deck. While the structural zone and floor-to-floor height for this option of 4.03 metres was not the lowest of all the options, it does not result in elevated cladding costs, as only the concrete post-tension flat slab option has a notably lower floor-to-floor height and therefore reduced area of cladding. The steel frame and precast concrete slab option has the second lowest total building cost. While it has the highest external envelope cost due to the highest floor-to-floor height of 4.2 metres, of all the frame options considered for Building 1, it benefits from low substructural costs due to the light frame weight, the lowest roof costs due to the use of a lightweight steel roof deck, and has the second quickest construction programme, which has resulted in reduced preliminaries costs. Conversely, the reinforced concrete flat slab option has both the highest frame and upper floors costs and highest overall building cost. It has the highest substructure costs of all Building 1 frame options due to the heavier frame weight, the highest preliminaries costs due to the longest construction programme, and also has higher roof costs than the steel options as the concrete slab construction continues throughout. The frame and floors cost is circa 10% higher than the steel composite option, and the total building cost is circa 6% higher. The post-tensioned concrete flat slab option benefits from the lowest floor-to-floor height of 3.95 metres, which results in it having the lowest external envelope costs. However, the heavier frame weight compared to the steel options means that it has higher substructure costs, and the longer programme also impacts on the preliminaries costs. This option also has higher roof costs than the steel options as the post-tension concrete slab construction continues throughout. Therefore, while this option has the second lowest frame and floor cost, it has the second highest overall building cost due to the impact of the frame on the associated building elements and programme. So in summary, the analysis of all four frame options for Building 1 has shown that the steel composite beam and floor option generates both the lowest cost and the quickest programme. This is followed by the steel and precast concrete floor slab option, and then the post-tension concrete flat slab, with the reinforced concrete flat slab option having both the highest cost and longest construction programme. The frame and floors for the steel-framed options could deliver up to a 10% lower cost than the other options, and the steel-framed options could deliver up to a 6% lower overall building cost. Looking at an average of the cost of the two steel options compared to an average of the two concrete options, the steel options are over 4% lower for both frame cost and total building cost compared to the concrete average. Furthermore, both steel-framed options can also be constructed in a shorter time, on average over 5% quicker. So we will now move on to look at Building 2, which is a typical speculative 8-storey city centre office building with a gross internal area of around 16,500 metres squared and a 3-metre clear floor-to-ceiling height. It is L-shaped with a double-height reception area, central core and internal secondary escape stair, as shown on the indicative cutaway and architect's impression images. The external envelope is a unitised curtain walling system constructed in storey height panels 1.5 metres wide with feature fins and solar control. The solid areas are lined with cold rolled metal steelwork, insulation and plasterboard. The building has been assumed to have 4 pipeline core air conditioning and mechanical ventilation, and allowances have been made within the floor-to-floor height for a 150mm ceiling and lighting zone and a 200mm raised floor zone.
So on the structural side, this building was designed to represent typical city centre office that you might find in central London. It had overall dimensions of 52 metres by 45 on an L-shaped plan footprint. And in both options, we had also assumed that they included basement, but this was assumed to be identical for both options and wasn't designed in detail. Again, the grid was the subject of much study and was set at 7.5 by 15 metres. But maintaining a 7.5 metre column spacing along the perimeter at all times. A 9 by 15 metre grid was also considered, but we felt that the 7.5 metre grid gave a more efficient configuration of half grids at the corners of the building, where a 9 metre grid would prove awkward. The 7.5 metre grid also coordinates better with car parking bays, as these are to be incorporated into the ground floor or basement of an office building. As far as structural options were concerned, again we chose 2 of the most common options used in office buildings. Option 1 was composite cell-form beams supporting a composite slab, and option 2 was a post-tension system consisting of downstand band beams supporting one-way spanning post-tension slab. So again, these options were taken forward and designed in enough detail to enable costing and programming of the construction. Again, looking at loadings, we assumed a 200mm raised floor for power and data distribution, along with suspended ceilings and services, giving a combined superimposed dead load of 0.85 kilonewtons per square metre, and imposed loads were again assumed at 4+1 allowance for partitions. Core construction was assumed to be steel cross-brace framing with blockwork infill for the steel-framed option and concrete core walls for the in-situ concrete frame. Bearing strata, as you can imagine in London with the basement, was assumed to be London clay, and the foundation type was typically CFA piles with 3 to 4 piles per typical column pile cap. The ventilation system was assumed to be conventional fan coil air conditioning with no natural ventilation. The ventilation zone for the concrete option was provided in a 400 deep zone beneath the concrete band beam, and for the cell form option it was an integrated zone with 400mm diameter holes at 600 centres in the cell form beams. The floor to ceiling height for this building was set at 3 metres, with the floor zone then determining the final floor to floor height for each option. Because most of the roof area was given over to plant room, the steel framed options retained the same composite deck at roof level, and the PT band beams and slabs were also retained at roof level. Plant areas were then partially enclosed by a steel frame structure. Again, in terms of results, we won't go into details of the steel or concrete sizes, but I'll look instead at the impact on floor-to-floor heights. The steel cell form option with integrated services came in with a floor-to-floor height of 4,180 millimetres. The post-tension solution with services below the band beams came in at 4,375 millimetres. So the integration of the service zone created a saving of around 200 millimetres per floor for the steel option. These steps then set the overall building height and allowed items such as cladding costs to be assessed for each option.
In terms of programming for Building 2, we've used the same methodology for analysis as per Building 1, namely all the common elements being kept constant throughout the analysis. Substructure works we've assumed will commence with a piling mat, followed by piling and so on through into excavation. The steel option and both the concrete and steel options are assumed to be built on a floor-by-floor basis rather than partially all the way up the building, which is more common for a building of this geometry and size. The program common durations are for the floor slab, which typically is 4 weeks, 3 days, and once again the cladding and the internal fit out, which is longer but more aggressive in terms of overlap for all of the options. The comparison then between the two systems as described are that the steel frame and decks is just under 17 weeks, and the concrete frame and slabs for the PT option are just over 28 weeks. And overall, therefore, the difference is much more pronounced because of the size of the building, about 72 weeks for the cellular and 80 weeks for the PT. And therefore the steel frame option has a significantly shorter frame and floor construction period, and the PT band and beam option 16 weeks compared to approximately 28. This obviously enables succeeding trades such as roofing works and internal fit out to commence earlier. The overall terms, the steel option therefore demonstrates about 12-week saving for the frame and overall 8 weeks for the holistic programs. In terms of logistics, because of the nature of the building and possible location, i.e. city centre. Both forms will be constructed using probably a luffing jib tower crane to avoid any oversailing constraints, and the concrete will be typically pumped up to the various floors.
Okay, just a quick reminder that questions can be submitted at any time during the presentation by using the box at the bottom of the screen. In terms of the cost comparison for Building 2, the same principles were adopted in the costings as for Building 1, with costs based on market testing and recently tendered projects, and all based at fourth quarter 2013 in the City of London. As with Building 1, fees, VAT, project contingency, FF&E, AV, Section 106 and 278 allowances are excluded from the study, and in addition, all costs associated with basement construction is also excluded, as it is assumed that this would have been a constant across all options, with the same construction adopted for both the steel and concrete framing options. To make sure that the study captures all implications of the frame choice, the costs of the substructure, roof, external envelope and preliminaries and the logistic strategies were individually assessed for each option alongside the differing frame and floor options. As with Building 1, those elements not considered to be affected by the frame material or configuration were assumed to be constant across both options, including the stairs, internal fit-out and finishes, and the mechanical and electrical services. It was assumed that a suspended ceiling is required across both frame types, with boxing in to internal steel columns and plaster and paint to internal concrete columns included. This slide sets out the key costs for the two frame options considered for Building 2, all expressed as a cost per metre squared gross internal floor area. Looking at just the frame and upper floor costs of the two options, the cellular steel composite option has a cost of £194 a metre squared compared to £210 for the post-tensioned concrete band beam option, a difference of around 8%. The cellular steel composite option also has lower substructure costs due to the lighter frame weight and reduced volume of foundations. The cellular steel option also benefits from a lower floor-to-floor height of 4.18 metres compared to 4.375 metres for the post-tension band beam option, which has resulted in a circa 5% lower external envelope cost due to the reduced area of cladding. The shorter construction programme for the steel option is also reflected in the reduced preliminaries costs. Overall, the steel cellular composite beam and slab option has the lower total building cost at £1,861 a metre squared compared to £1,922 a metre squared for the post-tensioned concrete band beam option. To summarise, the cellular steel composite option delivers both a lower frame and floor cost and a lower total building cost than the post-tensioned concrete band beam option. The steel option benefits from lower substructure costs due to a lighter frame weight, lower roof costs due to the cost of the steel deck compared to the post-tension slab, and from a lower external envelope cost as well as the lower floor-to-floor height. It also benefits from reduced preliminaries costs due to its shorter programme. Overall, the frame and floor cost of the steel option is over 8% lower than the concrete option and over 3% lower on a whole building basis.
So as part of the study, we also looked at the embodied carbon of the structural materials. And to put that into context, construction creates around 10% of CO2 emissions in the UK, and the operation of buildings, that's operational, creates about 50% of CO2 emissions. And with the ever tighter energy requirements in buildings due to Part L, embodied carbon is now the major component of those emissions for many buildings. So we now look at the embodied carbon on many projects, and we did so for this cost study as well. In terms of carbon factors, we felt that it was reasonable to use values either from the Concrete Centre or from the Target Zero studies, as we felt many consultants would look to these for source data. We used cradle-to-grave data as consistently as possible, and assuming that 99% of steel sections and 82% of rebar were recycled, and that 100% of concrete was downcycled to provide granular fill material. For concrete data, we looked at the so-called business-as-usual scenario, using 100% old Portland cement, and also looked at using 30% cement placement, which gave an appreciable benefit without compromising on programme. In this case, the results showed that the whole life embodied carbon, cradle to grave, was lower for the cell form option by around 19% in the base case and around 10% in the cement replacement case. The latter is probably more representative of general practice. Looking at the spread of all the results, the maximum value for embodied carbon was 253 kg of CO2 per square metre, which reduced to 204 by using cement replacement and was further reduced to 184 by the choice of steel frame option, which is an overall reduction of 27%, which is a very significant amount. That tonnage of CO2 is often equivalent to 10 to 20 years of renewables contributions to operational energy, and that can often be a good bargaining chip with planners in trying to economise on costly renewables, and we're hoping that this gets wider acknowledgement in regulatory systems such as BREEAM. Over to Alistair.
So to summarise, the study illustrates that for both building types, on a like-for-like basis, the steel frame solutions are highly competitive, with the frame and upper floor costs for the steel framed options being potentially up to 9% lower than the comparative options. The study has also highlighted the importance of considering total building cost, not just structural frame cost, as the choice of the structural frame material and configuration will have associated impacts on many other elements, including the substructure, roof and external cladding. The total building costs for the steel options are on average circa 5% lower than the concrete options as a result of the frame and upper floor costs noted above and smaller foundations, lightweight roofs, lower storey heights, reducing cladding costs and reduced preliminaries costs. Furthermore, the construction durations of the steel frame solutions are also shorter than the concrete frame buildings, up to 13% for building 1 and circa 11% for building 2. The study also considers embodied carbon for building 2, an element which is projected to become an increasingly important criterion for design options moving forward, and the study shows that in this area as well, steel frame solutions have a noticeably reduced embodied carbon compared to the concrete solutions, with an 18 to 30% lower embodied carbon total for the cellular steel option than the post-tension band beam option for building 2. The study has illustrated that steel frame solutions can outperform other common options and provide lower cost, shorter programs and lower embodied carbon. Well, that concludes today's webinar, with the exception of the last slide, which provides some useful links for further information, and we would note that the key points raised in the 2 cost planning webinars are expanded upon in the Steel Construction Cost Supplement, soon to be published on the steelconstruction.info website.